Hi everyone, Jonathan here. In this video, I will be giving you my take on section 6.2, which is about how we can use integrals to find volumes. We're going to be finding volumes of various new types of objects well beyond the usual objects we've got formulas for volumes for. And the basic idea, which you should have already read about, is how given some arbitrary volume hanging out in space, you can impose an x-axis. And if you can calculate the area of the cross-section at every value x, which gives you some function a of x, what you can do in order to approximate the volume, we're going to approximate it with slabs. Here each slab is going to be a right rectangular cylinder. So that means that it's kind of turned on its side here, but the base is on the side, and that it's got two bases with the exact same shape, and they form a right angle with the sides here. And here the sides are here and along the top and bottom. So when you go ahead and divide your interval AB up into a bunch of subintervals, and over each subinterval you approximate it with one of these slabs, assuming we know the area of the base, then the formula for the volume of a slab is just the area times the height. And here the heights are all delta x. And you wind up getting this lovely formula that the volume is going to be approximately the sum of the area of the bases, so the a of xi star, times the width, which is delta x. And by taking a limit, you'll get the exact volume, and that turns out to be the integral from a to b of a of x dx. This is a very nice formula, but in order for it to be useful, for one, we have to know the area of all the cross-sections. Like, for example, I'm a solid object. Suppose we tried to use this formula to find my volume. Well, suppose we impose the x-axis vertically going up and down, and for each height we can take a slice of me, and somehow we'd have to know what the area is. Like, what's that area of that slice of my head? What's this area of this slice around my shoulders? And so on and so on and so on. And for a human body, that's not going to be anything nice, or it's going to even be impossible to find. Furthermore, even if you can find this area function, it has to be a nice enough function that will actually be able to calculate its antiderivative in order to calculate the integral. One nice class of objects for which we can find that area function at each cross-section are what we call volumes of rotation. So a volume of rotation is formed by taking some area in the plane and rotating it about a line. Right now we're going to take this area in the plane, which is some area underneath the graph of y equals the square root of x, and rotate it around the x-axis. So if I adjust this slider, we can see the solid forming when I go ahead and do that rotation. And we get this nice paraboloid shape. Fun fact, this is actually the shape of headlamps in a car. Now we want to be able to find this thing's volume by approximating it with a bunch of cylinders and turning it into some kind of definite integral. So in order to do this, we're first going to take the interval over which we have area and divide it into a bunch of subintervals, and then approximate the area over each subinterval with a rectangle, like so. And right now I can increase the number of rectangles, and as you can see, we get a nicer and nicer approximation. However, things will look nicer if we just keep it at 3 for now. Now, to approximate the volume of the solid over this interval, we are going to rotate one of these rectangles around the x-axis. So when I move the slider here, we can see it rotating, and we get this very nice looking cylinder. And cylinders are, of course, something we know how to calculate the volume of. It's going to be the height of the cylinder times pi r squared, which is the area of the base. Now, by showing the solid, we can see that, sure enough, the cylinder is not perfect, but it is approximating the area of our solid object over the interval in question. So now we're going to show that process with where we rotate all the rectangles. And here we go, rotating all the rectangles, and we get this nice stack of cylinders. And then if I superimpose the object, we can see that the cylinders are making a decent approximation of the area of the object of rotation. In fact, as I increase the number of cylinders, you can see that we get a nicer and nicer approximation, a closer and closer approximation. So there's the cylinders without the object, and there's the object without the cylinders. And you can see that their volumes are about the same. So let me go ahead and just make one cylinder for you. So when we make a cylinder, we're actually using the right endpoint to get the radius of the cylinder, because it's just the distance from the x-axis up to the graph. And that distance is, of course, f of xi, where xi is the right endpoint. And that means that the volume of this one cylinder is going to be pi times f of xi squared. So that's pi times the radius squared times the height, which is delta x. And if we do that for every single interval, we're going to get a whole stack of cylinders, and the volume will therefore be the sum of the volumes of each cylinder. So it's going to be the sum from I equals 1 to n of pi times f of xi squared times delta x. And by taking a limit, then we're going to get the exact volume. So the volume of our underlying solid, which is now the integral from a to b of pi times f of x squared dx.